The discovery of the interstellar object 3I/Atlas has sparked an extraordinary wave of scientific interest because emerging data suggest that it is far more massive and significantly larger than expected for an object of its kind, placing it in sharp contrast with the first two interstellar visitors, 1I/Oumuamua and 2I/Borisov. In a recent collaborative study that I co-authored with Richard Cloete and Peter Verez, we examined observational data compiled by the Minor Planet Center between May 15th and September 23rd, 2025, focusing specifically on the motion of 3I/Atlas across the sky and comparing it to a purely gravitational trajectory. This comparison allowed us to set a strict upper limit on any deviation from gravitationally sculpted motion. Across 4,022 observations collected from 227 observatories, the total positional residual was constrained to just 0.028 arcseconds, meaning that any non-gravitational acceleration acting on 3I/Atlas, such as a rocket effect from outgassing, must be extremely small, capped at under 15 meters per day squared. This limit is crucial because it implies that despite the mass loss and outflow speed measured by the James Webb Space Telescope on August 6, 2025, the resulting reactive push did not meaningfully alter the object's trajectory, which in turn places a strict lower bound on the object's mass. From the Webb data, we know that the total mass loss rate was around 150 kilograms per second, with material escaping its surface at about 440 meters per second. If such a substantial outflow produced almost no detectable recoil motion, then the object resisting that recoil must be incredibly massive, at least 33 billion tons, based on momentum conservation. Translating this mass into physical dimensions indicates a minimum nucleus diameter exceeding 5 kilometers, assuming a solid density typical of cometary or rocky bodies. This estimate aligns closely with the upper end of the size range independently inferred from Hubble Space Telescope data, which suggested a diameter between 0.44 and 5.6 kilometers. Importantly, this lower bound on size also makes 3I/Atlas at least an order of magnitude larger than the interstellar comet 2I/Borisov, reinforcing the object's unexpected and anomalous nature. What deepens the mystery further is that 3I/Atlas's nucleus not only appears much larger than its predecessors, but also exhibits behavior and characteristics that complicate conventional interpretations. Throughout the observation period, high-resolution imagery from the Hubble Space Telescope on July 21, 2025, revealed an optically thin anti-tail pointing toward the Sun, an intriguing and persistent structure that remained visible through July and most of August. Later, on August 27, 2025, Gemini South imaging revealed the formation of a faint tail extending away from the Sun. Despite these coma and tail structures, which are typical of sublimating comets, the brightest point in every observation remains centered on the nucleus, suggesting that the centroid of the observed light is not being skewed by asymmetric bright spots or offset jets. This consistent alignment strengthens the reliability of the astrometric measurements used in calculating the upper limit on non-gravitational acceleration. Moreover, the elongated dust plume observed by Hubble, twice as long toward the Sun as it is wide, suggests a high degree of collimation in the outflowing material. Given the small 10-degree viewing angle, simple geometric considerations imply that the plume must have been about 10 times longer than its apparent width. Such jet-like behavior is typically associated with localized heating or venting, but even a strongly collimated jet should produce some measurable deviation in the object's trajectory if the body were small or lightweight. Yet 3I/Atlas remains stubbornly gravitational in its path, drawing us back again to the conclusion that only a massive, multi-kilometer nucleus could resist such forces. However, this enormous mass presents a puzzling contradiction when considered in the broader astrophysical context. If interstellar objects like 1I/Oumuamua and 2I/Borisov represent a typical population of smaller, sub-kilometer fragments ejected from exoplanetary systems, then statistics predict that astronomers should have detected hundreds of thousands of such small objects before encountering a giant like 3I/Atlas. Instead, only two small interstellar objects had been observed prior to this unexpectedly colossal one, implying a serious inconsistency between theoretical ejection rates and actual detections. This tension deepens if one assumes 3I/Atlas originated from the familiar reservoir of planetary system debris, because the mass budget of heavy elements available in typical planetary systems cannot easily support the frequent ejection of massive, multi-kilometer objects on the scale indicated by 3I/Atlas. Earlier theoretical work published shortly after the object's discovery already outlined this mismatch, but the new mass constraints intensify the issue dramatically. Future observational opportunities may help resolve these mysteries. The object will pass relatively close to Mars on October 3, 2025, offering the HiRISE camera on board the Mars Reconnaissance Orbiter a chance to acquire images with a pixel resolution of around 30 kilometers. While this resolution cannot reveal fine surface details, the amount of sunlight reflected from the brightest pixel could provide meaningful constraints on the nucleus's surface area and albedo, thereby refining size estimates. Additionally, on March 16, 2026, 3I/Atlas will pass near the Juno spacecraft as it orbits Jupiter, creating another observational opportunity as outlined in a proposal I co-authored with Adam Hibbard and Adam Crowell and supported in a letter by Representative Anna Paulina Luna. These encounters could decisively determine whether the nucleus is merely above 5 kilometers or significantly larger. If the true diameter is revealed to exceed this lower bound substantially, then conventional interstellar origin models, based on natural ejection of rocky material from planetary systems, could become untenable. Complicating the question of origin further are two notable anomalies. The object trajectory lies unusually close to the ecliptic plane, a rare alignment with only 1 in 500 likelihood for a randomly arriving interstellar object, and spectroscopic observations by the VLT team reportedly found nickel without iron in the material shed by 3I/Atlas. Such a composition mirrors certain industrially engineered alloys rather than natural cosmic materials, raising provocative questions. While such findings do not constitute proof of an artificial origin, they do open the door to alternative hypotheses involving non-natural processes or technological design, especially if future measurements reveal a maneuver or acceleration inconsistent with known natural forces. Given our stringent upper limit on non-gravitational acceleration, any substantial future deviation from a gravitational trajectory, particularly a sudden or directional one, could indicate the presence of active propulsion, which would be exceedingly difficult to reconcile with a purely natural body. Nonetheless, caution is essential. Even if 3I/Atlas exhibits unusual mass, unusual chemistry, and an unusual trajectory, we must avoid leaping to conclusions prematurely. Both a highly atypical natural comet and a technological object remain on the table as possibilities. It is entirely plausible that the surface of 3I/Atlas carries ices, such as CO2 and H2O accumulated during long periods spent traveling through interplanetary and interstellar space. In that case, the outgassing we observe might reflect not the object's core composition, but merely the transient chemistry of a surface layer, much like how the appearance of a book cover tells us little about its contents. For this reason, chemical measurements alone cannot resolve the object's nature definitively, nor should any single anomaly be taken as conclusive evidence. Only a comprehensive and multi-instrument dataset can provide the clarity needed. Ultimately, the unusual properties of 3I/Atlas challenge our assumptions about the population of interstellar objects and force us to rethink either the natural processes that generate and eject such bodies or the possibility that some objects may arise from technological activity beyond Earth. For now, the scientific method demands patience. More data will arrive soon from Mars and later from the Juno encounter, and each new measurement will help narrow down the possibilities. The coming months promise to be an exciting period of discovery, reminding us, as Galileo once emphasized, that truth emerges not from authority or speculation, but from careful observation and evidence. The nature of 3I/Atlas remains open, but one thing is certain. Its arrival has given us a rare and remarkable opportunity to learn more about the universe, and staying curious is the most important step toward uncovering whatever truth lies ahead.